Good morning, everybody. So if everybody has their laptop, I think today what we could do is to finish the theory on SARSA and Q-learning, and then switch to the implementation of these algorithms. So instead of switching to a new topic, we directly go to the lab session of this topic. I think it's maybe better for you. I don't remember though if I told you last time to bring your laptop today. So if somebody doesn't have their laptop, raise your hand and we can postpone the lab session to next Monday. Okay, everybody has a laptop. Okay, good. So let's quickly recap what we have seen last time. We started finally discussing how to do model-free control with standard classic reinforcement learning algorithms. We started from this idea that we need to switch from learning the value function to learning the action value function, which is the Q function, because since we don't know the dynamics, we cannot perform policy optimization using this expression because we don't know how to compute X prime. So we need to have Q so we can directly minimize that to obtain the policy. And then we started from the idea of actor critic method, which is basically what's behind policy iteration. So we start from a value, we evaluate it. No, sorry. Typically we start from a policy, but you could also start from a value, doesn't matter. You start from a value, you perform a policy improvement step to get a policy. And then from this policy, you can evaluate it to get a new value. And you keep going, iterating these two phases until you get hopefully the optimal policy. And this evaluation phase, you could also stop it midway somewhere so that it doesn't take too many iterations, and this still works. So exploiting this idea, we introduce our first reinforcement learning algorithm, which is called SARSA, which is an actor critic method. So SARSA basically works by learning the Q function using temporal difference learning. So these are the main equations that we have to know for learning the Q function. So at each step, we collect the current state, the current control, the current cost, the next state, and the next control. So we have these 5 elements for each transition we make in the environment. And we use these 5 elements for computing the TD error delta, which is nothing more than the classic TD error we have seen for value functions, but just here instantiated with action value functions. So you replace V with Q. And this error here is what you use for updating your action value function for that state and action. So you need the learning rate as usual, which is typically fixed. And this tells you basically how you can learn the action value. Then we need to decide how to choose the control. And with this example, we discussed that it's not a good idea to be always greedy with respect to the action value function, because if you're always greedy, then you end up not exploring anymore after very little time. And so a better idea could be to use an epsilon greedy strategy. So with a certain probability epsilon, we pick a random action. And with probability 1 minus epsilon, instead, we behave greedily with respect to the Q function. So sometimes greedy, sometimes random. So that we have a bit of exploration when we pick random actions, which we need, and a bit of exploitation when we behave greedily. And typically you start with epsilon being very large because in the beginning you have no information, so you want to be very exploratory. And then as the algorithm moves forward, you make epsilon decrease towards 0. Maybe not exactly 0, but close to 0. And then we discussed a bit the convergence properties of the algorithm. And then we discussed the fact that SARSA is an on-policy algorithm. So we need to collect data using the policies that we are currently learning. We cannot use data collected with a different policy in SARSA because of well, how it's designed. And these are the on-policy algorithms, which have typically low sample efficiency, because you can only use like recent samples that have been collected with the current policy, or a policy that was at least very similar to the current one. If the policy changes significantly, then the data is useless. So to improve sample efficiency, we started looking at instead off-policy algorithms, which are algorithms that can learn from data collected with any policy. So that seems a very good property. And the algorithm we discussed that has this property is Q-learning. So since SARSA was basically corresponding to policy iteration in terms of dynamic programming algorithm, you can think of Q-learning as corresponding to value iteration, which was the other dynamic programming algorithm we have seen. If you look at the equations of Q-learning for learning the action value functions, they're very similar to the equations we have seen for SARSA. So they look as a temporal difference learning update. The only difference is this term here, which is highlighted in yellow. And if you look at it carefully, you can see that the only difference is that instead of using the action that was really chosen by the policy, here we perform a minimization over all possible actions, and we select the best one. So there's a greedy action corresponding to the current action value function Q. That's the only difference. So very little in terms of math. Changes quite a lot the properties, however, of the algorithm. So because of this change, since we are not using the action that was chosen by the policy, this is no longer an on-policy algorithm, it's an off-policy. So we can use it with data that was collected with any policy. And indeed, if you look at the convergence properties of Q-learning, basically the only thing that we need is that we need exploration. So we need to make sure that the data that we are using for learning are sufficiently exploratory. So they should visit all pairs of state and action infinitely many times, or well, a sufficiently high number of times in practice. But you don't need the policies that you're using for collecting data to become greedy, as we needed in SARSA. So if you remember, in SARSA, we had also another requirement for convergence, which was this greedy in the limit. So the policy used for collecting data needed to become greedy in the limit. In Q-learning, we don't need that. We can just use an exploratory policy which does random stuff and still learn the optimal policy using that data. So that's the critical difference in practice between these two algorithms. We still need the infinite exploration and the Robbins-Monroe sequence of step size. Those are needed by both, but SARSA has this extra requirement for ensuring convergence. And again, these requirements are somewhat disconnected from reality, because in practice, we are not going to visit states and actions infinitely many times, of course. And the step size, we set it to a constant. We don't set it to this decreasing sequence. So that's not really what we do in practice, but this theoretical analysis informs us of what are the properties we can expect the algorithms to have, even in conditions which are not exactly matching the ones that we use in theory. And we're going to see that when we implement the algorithm, actually. Okay, so here I reported the pseudocode of SARSA and Q-learning. So this is going to be probably useful later when we want to implement them. With respect to what I've showed you last time, the pseudocode of SARSA is a bit different because I've made some changes to make it match the textbook implementation of SARSA, which was slightly different from the one I presented you last time. The difference is that now the update of the policy happens at every step instead of at every episode. That's the only difference. Apart from that, it's the same of last time. So in SARSA, what we do, well, we perform a certain number of episodes, K. For every episode, we reset the environment to a random initial state. We choose a control input from an epsilon greedy policy with respect to the current Q function. And epsilon here is going to start typically to 1. So basically, in the beginning, we're going to pick random actions. And then for all the time steps of the episode, we take a step in the environment, which gives us the next state. We also need the next control input for performing the SARS update. So we also choose the next control input, again, with an epsilon greedy policy. And now we have all the information that we need for performing the TD update, which is given by these 2 lines here. In the first line, we compute the TD target, so the Q target. And in the second line, we modify our current estimate of Q based on the TD error, which is this quantity here, multiplied by alpha, which is the learning rate. After updating the Q function, we just update the current state and control to be equal to what were the next state and control, so that when we restart here, we have the correct value of U and X. And we keep iterating, and typically at the end of every episode, we update epsilon to make it decrease to 0. How you make epsilon decrease to 0, that's up to you. You can decide to make it go linearly to 0 from the beginning to the end. Maybe not really to 0. Maybe you go to like 0.05 in half the episodes, and then you stay at that value for the other half. That's a bit of a heuristic choice. We can reason about that later. Q-learning, on the other side, it's a bit different. So it takes as input not only an initial guess for the Q function, but also a behavior policy, which can be anything. In practice, our behavior policy, well, we're going to work with epsilon greedy, but it's not going to be the same epsilon greedy that we use here, because while here we need to start with a large epsilon and then decrease, in Q-learning, pi b can be anything. So we could also, for instance, maintain epsilon very high for the whole duration, and it would still work. So we perform a certain number of episodes. For every episode, we reset the state to a random value at the beginning. Then we use the behavior policy for choosing the action to act in the environment. And this needs to be an exploratory policy. That's the only requirement we have basically for convergence. We take a step in the environment. We compute the Q target. And here we can see the difference in the math with respect to SARSA. So in SARSA, we evaluate Q at X prime, U prime. In Q-learning, we evaluate Q at X prime and choosing the action that minimizes Q. We update the Q function, and then we update the current state.
Could you repeat what do you mean with exploratory policy? I mean, epsilon greedy isn't an exploratory policy.
Epsilon greedy is an exploratory policy, but here in SARSA, you need eventually epsilon to go to 0 if you want convergence. In Q-learning, we don't need epsilon to go to 0. So for instance, we could still use an epsilon greedy, but maybe we start from 1 and we go to 0.5. We never reach 0. Or we could even remain at 1 the whole time. It doesn't matter. I mean, the algorithm still would learn the optimal policy. Then, of course, it would matter if we were collecting data on a real system, which we are not, because now we are collecting data in simulation. So if you're collecting data on a real system, then maybe you don't care only about finding the optimal policy, you also care about the performance of the policy during the data collection. And in that case, using an epsilon greedy with very high epsilon is not going to give you good performance during learning. So yeah, in that case, maybe it makes sense to make epsilon go to 0, even if you're using Q-learning, because you care about your online performance, not only about finding the optimal policy for later use. So that's a bit application dependent.
Yeah, an example of a policy that is not absolutely.
Yeah, I mean, a greedy policy is not epsilon greedy, for instance.
I mean, an exploratory policy that is not absolutely.
Well, you could just generate random actions with a given probability. That would be an exploratory policy. So an exploratory policy is a policy that has a non-zero probability for every action in every state. That's the definition. So it cannot be deterministic. If it's non-deterministic and it has non-zero probability for every action in every state, that's exploratory. And the most exploratory thing you could do is to assign a uniform probability to every action in every state. That's the most exploratory. And that's basically what you get with an epsilon greedy when you choose epsilon equal to 1. That's as exploratory as you can be. Okay, so these are the pseudocodes. And here is a slide summarizing a bit what we have said so far. So SARSA is an on-policy algorithm, whereas Q-learning is an off-policy algorithm. SARSA learns the Q function of the policy you're actually executing. And that Q function then accounts also for exploration. So if the policy you're currently executing has some exploration inside, so sometimes picks random actions, then the Q function accounts for those random actions because those are used in the TD update. On the other side, Q-learning learns the Q function of an optimal greedy policy, while executing instead another policy which is exploratory. So the Q function that is learned by Q-learning does not account for the exploration of the policy that you're actually executing. It's the Q function of an optimal greedy policy. So SARSA knows that the policy will sometimes explore and plans accordingly. Whereas Q-learning, you can think of it as if it pretends that the policy will be greedy in the future, even if it's not going to be greedy in the future. So in SARSA, the behavior policy and the target policy are the same because you're learning about the policies that you're actually using for acting in the environment, which means that the behavior policy needs to trade off exploitation and exploration. It cannot be completely greedy and it cannot be completely exploratory. Otherwise, SARSA doesn't work. So you need a policy which is a bit exploratory and a bit greedy, because you need a bit of exploitation and a bit of exploration.
That I run SARSA several times with different policies and see which one performs the best?
No, it just means that you need something like an epsilon greedy with epsilon decreasing. So you start with lots of exploration and then you gradually introduce a bit of exploitation. and you make that exploitation more and more dominant over the episodes. That's how you need to make it work. On the other side, you have a clear decoupling between the behavior policy and the target policy. And so the behavior policy just needs to ensure exploration. It doesn't matter if it's also a bit greedy or performing good. It can be completely random and learning still works. So this is what is going to make Q-learning in general more efficient than SARSA learning. And indeed, I mean, Q-learning came after SARSA historically as an improvement over SARSA. And here we have a summary of the key equations going actually from the very first lesson we did on reinforcement learning. So we can see on the left column all the equations related to dynamic programming algorithms. And on the right column, we have the corresponding temporal difference based algorithms. So here we have policy evaluation, which was based on the Bellman operator. So you update the value function at a given state as the cost at that state plus discount factor times the value of the next state. And if you want to do that with a TD style update, you do it like that, where this symbol here, arrow with the alpha inside, that it means that you update v of x towards this target using an alpha learning rate. This is also a shortcut for writing the usual TD update equation in a more compact form. Then moving to the control problem, we have policy iteration and value iteration. Policy iteration is an actor critic method and corresponds to SARSA. So in policy iteration, you alternate between these two updates, updating the value function, so doing a policy evaluation, which is basically the same as we see above, and doing a policy improvement step, which is updating the policy to behave greedily with respect to the current value function. And SARSA behaves quite similarly. So we have here the policy evaluation, but using temporal difference learning and Q functions. And below you have the update of the policy, which is no longer just greedy, but it needs to be epsilon greedy because we need exploration now since we don't know the model. We are in a TD setting, not in a dynamic programming setting. And so it's going to be greedy with probability 1 minus epsilon and random with probability epsilon. And last, value iteration is corresponding to Q-learning. So value iteration works by updating the value function using this expression here. It doesn't store the policy function. And Q-learning works by updating the action value function using this expression instead. And we can see that the equations are quite similar from the right column to the left column. The main difference is that you switch from V to Q, basically. So this is just a summary, since we have seen a lot of methods that look quite similar. I think it's good to have all the equations here on one slide so that you can clearly compare them and see spot the differences. Okay, so with this we have concluded the part on tabular reinforcement learning, so reinforcement learning using discrete action and state spaces. For next time, we're going to discuss how to go to continuous spaces, especially for the state, not yet for the control. But today we're going to use the rest of the time we have together for implementing actually for SARSA And then if you have enough time, also keep learning. So let's switch to Visual Studio. As I wrote on Classroom, you should update your code because I've slightly modified the implementation of SARSA and Q-learning. So make sure you're using the latest one. We are going to work in the usual folder, which is RL. And of course, we're going to start with exercise 4, which is SARSA. The implementation of the algorithm, as usual, should go in a different file, which is inside this solution folder, sol. And that's the name x4_SARSA_sol. We're going to work with the usual one joint pendulum. That's all we can afford. So this is a script, the main script. It contains a couple of utility functions for rendering the behavior of the policy in the viewer. And here we have a function for computing the value and the policy given the Q function. That's going to be useful later. And here is actually the real main function, which contains all the hyperparameters of the algorithm. So we have the number of episodes, how often we print stuff, the length of the episode, the learning rate, which is very, very large because we don't have any stochasticity in the environment, so we can use a very large learning rate. The discount factor 0.9, which is pretty small. This is going to help converging fast. That's why I set it so small. A flag for deciding whether we want to plot stuff. Epsilon is the epsilon that we use for the epsilon greedy. The initial value is 1 because we want to start from a completely random policy. And then we're going to decay with a certain speed of decay, which is dictated by this parameter here, epsilon decreasing decay. But we're going to always saturate epsilon below to 0.001. So that the probability of exploration never really goes to 0. We always maintain a bit of exploration probability, which is 0.1%. It's very small. Then we create the environment, which is our beloved discretized pendulum. We provide an initial guess for the Q function, which is just all 0 for every action and every state. So it's not a very smart initial guess. And we call SARSA. SARSA is the function that we need to implement and that is defined in the other file. Then SARSA actually returns only the action value function Q. It doesn't give us the policy. So what we do then is after we have Q, we compute pi from Q using the function defined above. So it's simply going through the whole state space, and for every state, we are taking the action that minimizes Q. So we compute the greedy policy corresponding to Q. Nothing special. And since we are at it, we also compute the corresponding value function. Just because the value function is easier to plot than the action value function because it depends only on the state, which in our case is a two-dimensional thing. So we can do a nice color map. Whereas plotting the action value function, we will need a four-dimensional plot, and we don't have any. So then we plot the value table, and then what we do is that we compute the real value function of the greedy policy. So we basically evaluate the policies that we have just computed, and we render it. So we apply it in the viewer and we see how it behaves, how it makes the pendulum behave. Okay, so if you run the code as it is, it should do nothing because the implementation of SARSA that you find in the other file is empty. So it just returns the same Q functions that you give it as initial guess. So it's not going to produce a very nice policy, of course, since it's 0 everywhere. So SARSA takes a bunch of parameters as input, but they are basically all the hyperparameters we have just discussed. So I think we don't need to discuss them further. And I think we can go directly into the implementation of SARSA. As usual, here you can find a list of comments which can guide us in the implementation. And the first thing that is already implemented is creating an empty list, which is going to contain the history of the cost to go of all the episodes. And we're going to use that to monitor if the algorithm is making any progress. We can expect the cost to go to decrease over the episodes on average. So we need to do a for loop for every episode. So for app in range and episodes. We reset the state of the environment. So m.reset. And then we compute U with an epsilon greedy policy. So for the epsilon greedy policy, you can see I've already implemented here a little function which implements the epsilon greedy strategy. So it samples a random number with a uniform PDF from 0 to 1. Is this random number is below epsilon, and that's going to happen with probability epsilon, of course. It returns a random integer between 0 and u minus 1. So it returns a random action. Otherwise, it returns the greedy action, which is the minimizer of the Q function for the given state. So this is how you implement epsilon greedy. So we're going to use it here. U equal epsilon greedy. And then we can start the episode. So for T in range max episode length.
What exactly is NU again?
NU is the number of actions.
Give that to episode greedy
because it needs to sample a random action. So the actions here are just integer values between 0 and the maximum number of actions that you have.
I see.
So in our case, we are discretizing the actions of the pendulum to 11 values. So it's going to give us a random number between 0 and 10.
So this, there are nothing on my blood. Okay, thank you.
So 0 is going to correspond to the minimum torque. 10 is going to correspond to the maximum torque. 5 is going to correspond to 0 because it's the value in the middle.
But if I had like more than, let's say, one joint, I'd have to do it for every single joint, right? So
Yeah.
And U would depend on where I am in the row.
No, so if you have like a 2-joint robot,
yes,
and you want to apply the same discretization, so 11 values for the whole range, then you're going to have 11 to the power of 2 possible actions, because you can choose any action between 0 and 10 for the first joint and any action between 0 and 10 for the second joint. And so the total combinations,
It's joints and do the completeness of interval. Yeah, okay.
so it's going to increase exponentially with the number of joints. That's why it doesn't scale.
Yeah.
And that's why we do it for a one joint robot in class. And it's even worse for the state, because the states, you add two variables every joint, because you have position and velocity.
Yes.
So you need, first of all, to take a step. So x next and cost equal m dot step u. Then we have x next, but we also need u next for performing the TD update. So u next, again, we're going to compute it with an epsilon greedy strategy. And now we can compute the Q target. So Q target is just the cost plus the discount, which is gamma, times Q evaluated at the next state and the next control. And now that we have the Q target, we can update our Q function. So we just add the learning rate times the Q target minus the current value of Q. And last, we update x and u to be equal to x next and u next. So you can see it's very similar to the pseudocode we have seen a moment ago. We just need now to update epsilon after every episode, because we need epsilon to decrease over the episodes. Otherwise, we are not going to converge, because we need the policy to become greedy as the number of episodes goes to infinity. So as the comment suggests, we're going to use an exponentially decaying function for updating epsilon. So the idea is to say that epsilon is equal to np.exp, which gives you the exponential, to the power of the decay, which is called eps decreasing decay, times the episode number. And then we also want to make sure that we are not going below the minimum value of epsilon, so we perform a saturation. We also need to keep track of the cost to go, because we want to have this list of cost to go to return for just analyzing the behavior of the algorithm. So we're going to create a a variable j, initialize cost to go. But we need to remember also that the cost to go that we want to compute must be discounted. So here we should have in front of it, we should have gamma to the power of t. And so we can just add it here. And now we just do some prints. So we're gonna print the episode number. We can print the mean value of the value function, the mean value of the cost to go, and epsilon. So epsilon is easy. Mean v mean cost to go. So the episode number is ep. Then we have epsilon. Then we can compute the mean value, which we will need to compute before this line. And p dot mean of the history of cost to go. And it complains because I haven't computed v, but I can easily compute v by using the function that was defined here. I'm just gonna copy this. I don't need to copy, sorry. I can just call it because that file is included in this one, so it should be visible. So it's going to be v equal compute v pi from q, which takes as input the environment and q. So m, q. It's going to return both v and pi, actually. Epsilon, I'm going to multiply times 100, so we get a percentage. And that's it, I would say. Well, we have also the plot thing. So we can say if plot and dot, so the environments have this function for plotting the value function, which is called plot vtable. So we can do that plot. And that's it.
Why do we need to evaluate J inside the second for loop and not just use H CTG? Because it doesn't really make a difference, does it? Because we're not many like that at all. So it's first.
So HCTG contains a list of J's.
And J is the
Is the cost to go, yeah, is the total cost of an episode. So it's the summation of the cost at each step of the episode, discounted with gamma.
Yes. But could we do this? I mean, we could do the same in just HCTG, but just using the last entry.
But HCTG is a list.
Yeah. So we could just use, I mean, we append J to the list and we could just use HCTG.
The last element.
Just always use it as.
Yeah, it's the same. But I don't see an advantage.
I don't know either.
Yeah, I mean, you could do it. You could do it, yeah. Okay. I think we are ready to test it. Python X4 SARSA. Let's see if it works. One never knows. So it's running, which is already something. We can see epsilon started from 100%, and then it's going down, and towards the end it's at roughly 1%. So that's the probability of exploring. This is kind of what we wanted to achieve. We can see that the average value of the value function started from 0, and then it went down to minus 1.8, which is an improvement. Since we are minimizing a cost, the value should decrease. And also the average cost to go of the episodes is going down. So we started from 0, and then slowly it's going down, and at the end it's roughly minus 1.5. So this value that we are seeing here, I guess it's a value that corresponds to the action value function computed by SARSA. You should compare it in your mind with the values that we had for the same pendulum environment when we were doing like value iteration or policy iteration. And if you have roughly that image in mind, you may remember it was not really like this. I mean, you had a clearer area here, which was corresponding to all the states from which you could directly reach the top position of the pendulum from one side, and you had another clear area here. I mean, we can kind of see that there are some clear spots more or less in this diagonal, but they're not as clearly defined as in the truly optimal policy, which suggests me that this is, I mean, we haven't really converged yet to the optimal value function. But that was actually only the value corresponding to the action value computed by the algorithm. But then if we take the policy that is greedy with respect to that action value and we evaluate that policy, then we get this, which already looks a bit better, because now this diagonal band is much more visible. So Doesn't tell us how good it's behaving, but at least we can see the structure is similar to the optimal policy. So there are these states here in this diagonal band, starting from which the value is much smaller than outside this diagonal band. So which means that if we start from this, so the policy is going to probably behave pretty well. Then we can also render the policy in the viewer. And this is the average cost to go during the iterations. And we can see that indeed there is an improvement. We could see it even in looking at the prints in the terminal, but here we see it with a finer grain. And we can see we went from 0 to minus 1.6. And minus 1.6 is here we are computing the average. Sorry, no, we are not computing the average. So this is really the cost to go, I think, of the episodes. And we can see there is a clear trend of improvement. There is no averaging here going on. This is just the cost to go for every episode. And these values here that are printed, I think they are very good to keep in mind for later when we're going to implement Q-learning and we will want to compare it to SARSA. So these are the values that matter. Compute real value function of greedy policy. And the real value function of the policy that we obtain has an average value of minus 3.5. So that's going to be our main number to compare this with Q-learning. And the question is going to be, can Q-learning get a policy which has a better average value than this one? Of course, using the same number of episodes. Who knows? We will have to check. So what we can try to do is to make the algorithm run for longer. And maybe we can also enable the plots. And we could also open the viewer so we can render the policy in the viewer later. Let's see what we get. So, okay, now the viewer is opened. This is the initial value function, which is just 0 everywhere. Not very interesting. So this is the value after 500 episodes. And in the beginning, it starts learning something only close to the top position. After 1,000 episodes, we have this. 1,500, 2,000, 2,500. You can see that it's getting clearer and clearer. 3,000. And you can see that the average value is also decreasing. So before we stopped here at 5,000, but now we will keep going. And indeed, we can see that there is still improvement. So we were not at convergence when we stopped. Still going down, minus 3.4. Maybe now it has converged. Okay, so we reached an average value of minus 3.4. And this is the real value of the policy that we get. It's pretty good. It's not as clean as what we were getting, of course, with dynamic programming, because here we have a much less uniform exploration of the state space. And indeed, we can see that there are some spots where we have some darker colors. These are probably suboptimal states. So states for which the policy has not converged to a good policy. And so the performance starting from this state is not going to be good. Whereas if you start just from the state next to it, it's much better. And now the cost to go, we can see it goes to much smaller values, minus 2.6. Whereas before we were at minus 1.6. So we went much, much lower. Okay, it also renders the policy, but we missed it. Next time. And again, the value that we want to keep in mind is this one, is minus 3.6, which is better than what we had before, but not much. Before it was minus 3.5. So we are quite close. Okay. Then of course we could play with hyperparameters of the algorithm. We could play with the learning rate, and it doesn't make much sense to play with the learning rates. We don't have any noise in this environment, so it makes sense to use a very aggressive learning rate close to 1. The discounts is not really a hyperparameter of the algorithm. That's a parameter of the problem definition. I mean, you can still change it, but it's not part of the algorithm. The main parameter we have here to play with, if you want to change the behavior of the algorithm, is how quickly we want epsilon to go to 0. And here we could just test a few things. For instance, what happens if we make epsilon go to 0 too fast or too slow? So for instance, what happens if the policy does not become greedy? For instance, if we set the minimum value of epsilon to be 0.9, so the policy is going to remain like mainly exploratory, because 90% of the times it's going to pick random actions. Well, let's see. I'm going to disable the plots because they're annoying after a while. So you can see that epsilon started from 100, it went to 90%, and then it remains at 90% because that's the lower bound that we have set. And you can see there is no improvement. Nothing is improving. So if you use a very exploratory policy which doesn't become greedy, then there is no learning, no improvement. Which makes sense. I mean, it checks with what we have seen before in theory. So that's the value function that we get at the end. It's not good. It only learned very close to the target state. So this is the real value function of the greedy policy, which is actually not too bad. So the average cost to go is basically remaining very close to 0. I'm surprised here by how good this is. Let me check if it's doing what I thought it was doing. It's doing policy evaluation on pi. And pi is the policy computed from Q, which is the one we get here. Okay, for some reason it's doing okay, the final policy, even though during the algorithm, clearly the values that it learned was not doing okay. It may be just by pure luck. So we can try the other extreme, which is what happens if we make epsilon go to 0 too fast. So I've reset the minimum epsilon to a very small value, which is 0.001. And then we can just make epsilon go to 0 very fast. So I increase the decay rate to 0.1. And we can run this again. So basically, it went straight from 100% to 0.1%, which means that it's quite greedy. It's mostly gridded. So this is exploring still a little bit, but very, very slowly. So if we compare these values here, which are more or less constant at -1.8, with the values that we were getting before, we can see that before it was much better, because the value was getting to -3.4, and now instead we are stuck at -1.8 and 1.9. So clearly, since the policy is behaving very greedily, there is not enough exploration, and it's not able to learn effectively. So to make SARSA behave well, you need to make epsilon go to 0, but not too slow and not too fast. Otherwise, progress is going to be very, very slow. And unfortunately, there is no one telling you how fast that should be. So that's really a hyperparameter that you need to figure out on your own how to tune. Okay. I think we can take a break now, 10 minutes. And then after the break, we move on to the implementation of Q-learning. So I'll see you back here at 50. Before moving on to Q-learning, I wanted to show you the behavior of the policies that we are computing in the viewer. Because looking at the value function is very exciting, but maybe we also want to see how the robot behaves. So I'm rerunning the algorithm with the standard settings for the epsilon decay. So that one that was giving a good behavior. So now what's going to happen is that the robot is going to be reset to a random initial state, and the policy is going to be used for controlling it, and it's going to do this for 10 times. So we see a bit from 10 random initial states how the policy makes the robot convert to the top configuration. You can see that it's doing the swing up. In that case, it failed because it didn't reach the target. Also, this case it failed, but we can see that it's actually going there. It's just taking a bit longer. This time it succeeded. Again, it succeeded. This was easy. No swing up needed. Even easier this time. This was nice. Okay, so we can see that it's working. The policy we are computing is actually working. It's not just producing a nice value function, it's also doing something. Okay. So that's all for SARSA. We can now close this and move on to the next one, which is Q-learning. And Q-learning, well, it's going to be very similar because actually you have seen that the algorithms are quite similar in terms of math. The main script is basically the same. The only difference you're going to find is that this time I've set the minimum exploration probability to a very large value, which is 0.5, because in Q-learning, we know that we don't need to have greedy in the limit. The rest is basically the same. The solution needs to be implemented as usual in this second script, which contains just an empty template for the Q-learning function. You can find as usual here the description of the algorithm. And I suggest that this time you take the lead and you implement it. You can start, of course, from the implementation that we just did for SARSA because they are very similar. So I think that starting from SARSA, it should be pretty efficient for you to implement Q-learning. And we have a half an hour. So I say you take the whole half an hour for working on the implementation on your own. And then next time we do the implementation together for those who haven't managed. So you can start working on that.